Hello everyone, welcome to this video. In this video, we'll be solving question 14 from miscellaneous exercises. So here in this question, they are saying if S be the sum and P be the product and R be the sum of reciprocals of n terms of a GP, we need to prove that P square R raised to power n is equals to S raised to power n. So this thing we need to prove, right? So let's first of all define what is our GP having n terms. So if we have A as the first term of this GP and small r as the common ratio of this GP, then the first n terms would be of this form. The first term would be A, the second term would be AR, the third term would be AR square, and the last term would be AR raised to power n minus 1. Why? Because you know the general term is given by AN is given by AR raised to power n minus 1. So all the members here are represented in terms of the first term and the common ratio, correct? So here we are given capital S to be the sum. So that means we are given small a plus AR and so on up to AR raised to power n minus 1. This thing is equals to A into R raised to power n minus 1 divided by R minus 1. If we are assuming this R to be greater than 1, right? We are assuming this thing, correct? So let's mark this as equation 1. Now they are saying this product of all the terms is P, right? And how many times this A is appearing here? We have in total n terms, so A is appearing n times, so it would be raised to power n. A would be raised to power n. What about R? For R, there is no R. We can write R raised to power 0. So when you collect all the R's, you would have R raised to power 0, R raised to power 1, R raised to power 2, and so on up to R raised to power n minus 1. So we may write it as R raised to power 0 plus 1 plus 2 plus so on up to n minus 1. Here we can solve this expression and calculate what is this sum. Now if you notice that this forms an arithmetic progression, right? And you know how to calculate the sum of such an arithmetic progression, right? So here this is an arithmetic progression with we are leaving this term, so we are taking this as the first term, right? And the total number of terms then would be n minus 1. So here A is equals to 1, right? We are going up to n minus 1 terms, and what is the common difference? The difference between each term is again equal to 1. So we have this as equals to n minus 1 divided by 2 into 2 into the first term plus how many terms we are having? N minus 1 minus 1 into 1, because D is the common difference, which is 1. So you can simplify this n minus 1 upon 2, right? And then you have 2 here, and when you solve this you would have n minus 2 here. So this 2 and this 2 gets cancelled, so you have this as the answer, this as the sum. So you can substitute the sum here. Instead of writing it like this, you can substitute the value here as n minus 1 divided by 2, correct? So let's mark this as equation 2. Now what about R? Given capital R is given to be the sum of all the reciprocal of the terms. So we would have 1 upon A plus 1 upon AR plus 1 upon AR square and so on up to 1 upon AR raised to power n minus 1. So this again forms a GP with the first term as 1 upon A, and the common ratio, we can calculate the common ratio here by dividing this term with this term. If you divide them, you would obtain 1 by R as your common ratio. So it's very easy to calculate this sum and the value of R by using the sum formula for the GP. And according to the formula, you would have A, the first term, into 1 minus R raised to power n upon 1 minus R, this formula when this R is less than 1. Remember, this R was greater than 1 here for this GP. So what would be the value of 1 by R? It would definitely be less than 1. Hence our common ratio, this is less than 1, correct? So if this is less than 1, we may use this formula in order to calculate the result. So that this is our first term, 1 minus this is our common ratio raised to power n, because the total number of such terms are n, divided by 1 minus the common ratio, which is 1 by R, right? So let's mark this as equation 3. Now we have to prove that P square R raised to power n is equals to S raised to power n. So let's take this left hand side first, P square R raised to power n, right? So let's take the value of P, which we have calculated here to be A raised to power n, R raised to power n, n minus 1 divided by 2. So when you take this and write it here. What do you have? You have this term, and similarly you can write the value of r, and then this is the value of r, and then you can take its power n. Now what we have to do, we have to simplify this, and we have to see whether this forms equals to s raised to power n or not. So let's have a look here. So you can multiply the powers here. N into 2 is 2n, right? Again here, when you multiply this term with this term, this 2 and 2 gets cancelled, so you are left with n minus 1. And here you have 1 upon a raised to power n here. Here this term raised to power n, and this term raised to power n. This term also raised to power n, and you shift it inside, correct? So here it would be 1 upon a raised to power n. Then you can take the LCM here. You can separate the powers, 1 raised to power n and r raised to power n. 1 raised to power n is just 1. R raised to power n is, you can take the LCM, so it would be r raised to power n minus 1 upon r raised to power n. And here also you can take the LCM. When you take the LCM, you would have r here. So this term, because it is present in the denominator, it would come in the numerator by reciprocating it and multiplying it, right? So it would be r divided by r minus 1, whole thing raised to power n. Now we have to simplify the terms, and we can do that by taking up the common terms and like terms together, right? So here you see, here we have a and here we have a. So we would have a raised to power 2n minus n. So it would be a raised to power n only. So this is our answer for a. What about the next term? The next term is about r. So we have 1 r here, 1 r here, 1 r here. So you have to take all the r's together and then calculate it. So the r is here, the base is common, so powers could be added and subtracted. So it would be n minus 1 here. Then n into n is n square, but this thing is present in denominator, so we would have minus n square. And then here r raised to power n is there, so we have plus n. So you can solve and simplify this so that you would have you can take n common from each of the terms, so you'd be left with n minus 1 minus n plus 1. So you see this and this cancels, this and this cancels, so the power becomes 0, right? You would have r raised to power n into 0, which is r raised to power 0, and anything raised to power 0 is 1. So this term actually vanishes here, correct? What about the other terms? The other terms they are remaining is r raised to power n minus 1 whole raised to power n. This we have copied down exactly, and we are left with this term r minus 1 whole raised to power n. This we have also copied down exactly, correct? So this term vanishes, so we are left with this much portion. So let's write it here. Now you have power n on each of the terms, so you can take the power n as common, and if you see what is this, this is your s. A r raised to power n minus 1 divided by r minus 1. This is the value of s. So you can substitute it here, and you would have s raised to power n, which is your right hand side. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.